In our discussion of ODE solvers, we have talked about first order ordinary differential equations so far. How can we apply these techniques for higher order initial value problems? The basic idea of applying the techniques such as Euler method or Runge-Kutta method to higher order problem is that we take a higher order ODE and we convert it to a set of first order ODEs. Then these first order ODEs, usually they become coupled. This coupled ODE we solved simultaneously. So instead of yi plus 1 equals yi plus h by 6 k1 plus 2k2 plus 2k3 plus k4 type fourth order Runge-Kutta algorithm, now I have y subscript j here and also k subscript j here. Each of this j indicates one of these first order ODEs. So let us see this technique with an example. Let us consider an ordinary differential equation initial value problem where we are interested to find out y within the interval x 0 to 1, where at x equal to 0 the initial conditions y and y prime are given, and my ODE is given by y double prime minus 2y prime plus 2y equals e to the power 2x sin x. So first we have to break it down into two first order ODEs. I take up u1 and u2 are two new variables where y is u1 and y prime is u2. Therefore, this ordinary differential equation now I break. The first break is, this is u1 prime equals, u1 prime means u1 is y, therefore u1 prime is y prime and y prime is u2. So u1 prime is a function of x, u1, u2, and this is just u2 here. And u1 at x equal to 0 is minus 0.04. This is my initial condition. Here I have the ODE, first order ODE, initial value problem. I don't know the right hand side u2 here, but u2 does have its own equation. So I come here and y double prime is equal to u2 prime because y prime is u2. So I write this equation as u2 prime equals some function of x, u1 and u2, and that will be given by this e to the power twice x sin x, which is already there, and then this 2y prime, I take it on right hand side, y prime is u2, so it gives me twice u2, 2y, y is my u1 minus 2u1 plus e to the power 2x sin x. So this is the equation of u2, and you can see that this is once again a first order initial value problem. u2 at x equal to 0 is given as minus 0.6. So now you can see that we have these two ordinary differential equations, both are initial value problem. However, in the first equation we have u2 on the right hand side, which we don't know. In second equation we have both u2 and u1. We don't know the u1. u1 will be given by the other equation. So essentially these two equations are now coupled. So instead of one second order ODE, we have two coupled initial value problems, and we can solve them together. This is the approach we will take no matter whatever is the order. We are talking about second order, but even higher order problems can be broken like this. If this is a third order ODE, then we will have three first order ODEs. Now how we are going to solve it? So let us apply the fourth order Runge-Kutta, because mostly this technique we will use in initial value problems. So let's see how we'll go about it. If we have one equation, one unknown, then we know that we start Rangakutta using this. You remember that the general algorithm is that yi plus 1 equals yi plus h by 6 to k1 plus 2k2 plus 2k3 plus k4. And this k1 is given by f xi yi. This comes from the fact that this is y prime is f of xy. For this sort of equation, we have this k1 is f xi yi. Now if I have two equations, then what will happen? I will have 2k1, one for each equation. I have two equations here, u1 and u2, so I will have 2k1s. So that will be given by this k ji. J will be 1 and 2. So k for equation 1 will be k11, k1 for equation 2 will be k21, and they will be given by f. Here I have this j will be 1, and then I have xi, u1i, u2i. Similarly, I know that k2 for this particular y prime equals f xy. I know that k2 is f xi plus h by 2 yi plus h k1 by 2 in usual fourth order RK. Now we want to bring two equations. So what will happen? We will have two k2s, and that is why we are writing here kj2. J is this 1 and 2. 1 for equation 1, 2 for equation 2. So this is our equation 1, and the second equation is our equation 2. So k for equation 1 is, this is once again, this is k12, that would be given by f1, that is here, and then xi plus h by 2 ui u1i plus hk11, k11 we have already calculated here by 2, u2i plus hk21 we have already calculated here because k1 we have calculated. I know k11 and k21. I plug it in here and I get two values of k2. Similarly, we can calculate k3, which we know that for y prime equals fxy, that kind of equation we have fxi plus h by 2, yi plus hk2 by 2, and then kj3, where once again j goes 1 and 2, 1 for equation 1, 2 for equation 2. So k13 will be given by f1 xi plus h by 2 u1i plus hk12 by 2, and k12 we have already calculated over here in kj2, and u2i plus hk22 by 2, 22 also I have calculated here. And finally we can have this k4 as kj4 fj xi plus h u1i plus h k13 I am calculating over here, hk23 which will be added to u2i, k23 is calculated over here. So now I have all the k's are calculated. We are now ready to update this u1 and u2, and let's see that how we will do so. Remember, this is our original differential equation, and I have broken down in these two equations right here with two initial conditions, and we have seen that this is how we can get the k, 4 k's for each equation. After I calculate all these k's, I can now update u1 I plus 1 will be u1i plus h by 6, k1 plus 2k2 plus 2k3 plus k4. All these are coming from this k11, k12, k13, k14. Similarly, for u2 I plus 1, I'll have u2I plus h by 6, k21 plus twice k22 plus twice k23 plus k24. So please note that here when you will calculate k, you have to calculate k1 for both j1 and 2, then only you can go for k2, j1 and 2. Once you have k1, k2 both are done, you go to k3. So each k when you take, you have to iterate over this, not iterate, but you have to evaluate over both j's, and then only you can go to the next k. Once you update u1 and u2 like this, you should be able to plot the results. In this case, this particular differential equation can be solved analytically. Luckily, this is our solution that you can try yourself. And then this is coming from the numerical solution, the black line, where these red dots are analytical. You can see that it matches very well here. And if your solution is all right, step size is all right, it should match that nicely in most cases. You can generalize this idea for nth order initial value problem. You can take this u as a vector and k as a matrix and then a as a vector. So u vector is this is a column vector of u1, u2, etc. up to un. I am writing here as row, that is why there is a transpose, because this is a column vector. And k will have n of this. You can see that this is an nth order equation, so I have n first order equation. I have this u1 to un here, and similarly k will come here with n rows and 4 columns. K will be multiplied with a, which are actually constant, h by 6, h by 3, h by 3 and h by 6, and this is how you can update no matter whatever the order of the differential equation is. You can now try a simple exercise. Some of you may be familiar with this sort of equation from fluid mechanics. Here I take this equation at x equal to 0. We have y equals 0, y prime equals 0 and y double prime equals 1. And then I have y triple prime plus half of y double prime equals 0. I want to solve this equation for x going from 0 to 10. I'll discuss something about this equation in little more detail, but if you have studied fluid mechanics, you know that this type of equations are useful in solution of laminar boundary layer over flat plate. But even if you don't know all this physical application, you can still solve this equation and check the results, how they are coming. Here you solve it using a 4th order RK. It's very important that you understand this method for multiple ODEs. That is why this exercise is very important, and you use a step size of 0.01. After that you plot y prime and y double prime versus x in the same plot as I have shown in previous slides. So that's all for this lecture. Thank you, and I'll see you in next class.